Hi, I'm DJ Dimorin and I'm a student from Mapua University, and I'm here to discuss about thermal analysis of differential scanning calorimetry or DSC and thermo-gravimetric analysis or TGA. What is thermal analysis? It is a branch of material science where properties of materials are studied as they change with temperature. It is also defined as group of methods by which the physical or chemical properties of a substance, a mixture, and a reactant are measured as a function of temperature or time whilst the sample is subjected to a controlled temperature. There are certain types of analysis that can be categorized to what indications or parameters should be analyzed. In this diagram, as you can see, first is mass, where you can use thermogravimetry. The second is a temperature or heat flow. It's a difference thermal analysis or DTA, and also a differential scanning calorimetry. The difference of that analysis is that in DTA or difference thermal analysis, specifically you can analyze the temperature difference, while on the DSC or differential scanning calorimetry is for enthalpy. On the other parameters, there are for dimensions, we could use thermomechanical analysis or TMA, and also DMA or dynamic mechanical analysis. And there are also TOA or thermo-optical analysis for optical properties, and TS or the thermosonimetry. In this presentation, I'm only going to focus on DSC and TGA separately. But first, we should know the basic principle behind thermal analysis. Here are the basic principle of in a diagram of thermal analysis. First, there is a sample holder or compartment for the sample. Second is a sensor to detect, measure the property and temperature of the sample. Third is an enclosure, which the experimental parameters may be controlled. And lastly, a computer unit or computer to control data collection and processing. Now, what is differential scanning calorimetry or DSC? DSC is a technique developed by E.S. Watson and M.J. O'Neill in 1962 and commercially introduced in 1963 at Pittsburgh Conference for Analytical Chemistry and Applied Spectroscopy. In this technique, energy is necessary to establish a zero temperature difference between the sample and reference material, for which it is measured as a function of temperature. As a sample and reference material are heated by separate heaters, their temperature are kept equal while linearly increasing or decreasing. This technique is widely appropriate for measuring glass transition temperature and characterization of polymer, or also an amorphous part of a crystalline polymer from hard, brittle to state to soft, to a brittle state to soft and rubbery state. Here shows a typical DSC curve of heat flux versus temperature or by time. As you can see here, there are two conventions made for two conventions, exothermic and endothermic. For an exothermic reaction or exothermic reaction or exothermic part, a sample may have positive or negative peak depending on the kind of technology used within the experiment. Through DSC, enthalpies of transitions can be obtained by integrating the peak of corresponding to a given transition. There are also factors that could affect a DSC curve, which are in the factors for the instrumental is the furnace heating rate, the recording or chart speed, the atmosphere of the furnace, the geometry of the sample, the geometry of the sample holder or location of sensors, the sensitivity of the recording of the system, and the composition of the sample containers. Those are the categorized as the instrumental factors. Now for the characteristic of the sample, one is the amount of sample, the nature of the sample, its sample packing, the solubility of evolved gas in the sample, the particle size, the reaction to heat, and the thermal conductivity. DSC can be very advantageous for certain conditions, such as instruments can be used at very high temperatures. Instruments are highly sensitive, flexibility in sample volume or form, characteristic transition or reaction temperatures can be determined. High resolutions can be obtained, high sensitivity, and stability of the material. But also, it can also have a disadvantage too, or limitations. The limitations of DSC, it is generally unsuitable for two-phase mixtures. There can be difficulties in test cell preparation and avoiding evaporation of the volatile solvents. It is also generally used only for thermal screening of isolated intermediates. It cannot detect gas generation, and there can be uncertainty of heat of fusion and temperature transition. Now that is for DSC. Now, therefore, we have the TGA or thermo-gravimetric analysis. What is thermo-gravimetric analysis? It is a type of thermal analysis which examines the mass change of a sample as a function of temperature for scanning mode or as a function of time for as future mode. In this thermal analysis method, changes in physical and chemical properties of materials are measured as a function of increasing temperature rate or as a function of time. But how does TGA works? TGA works in this schematic diagram of thermogravimetric analysis. The main principle of TGA is that the mass of the substance is measured as a function of temperature while it is subjected to a controlled temperature, program resulting in TGA curve. The controlled temperature ranges from 0 to 2000 degrees Celsius. This is the change in the mass of the sample studied by different physical or chemical transition. Transitions may occur typically as physical transition. These are adsorption, desorption, sublimation, evaporation, and vaporization. It can also be typically as chemical transition, which are oxidation, reduction, chemosorption, loss and drying, and degradation. This technique is appropriate for analyzing volatile products, gaseous products lost during the thermoplastics, thermosets, elastomers, films, fibers, grains, and etc. Here shows a TG curve from analysis of CS or GO, CSGO composite films, while this one shows the TGA curve of pure carbon fibers and silicon carbide nanofibers coated in air. TG curves may be affected by these following factors, categorized as mainly instrumental factors for the following: furnace heating rate, atmosphere, the furnace. These affect the composition temperature of the sample and the sample holder. The sample holder as a factor for the characteristic of sample, we have weight of the sample. It is always recommendable to have a small weight of sample. Sample particle size, just like the size, small and uniform particle size is highly recommendable. If not, apparent rapid weight loss may occur. Another characteristic of sample is a reaction to heat, compactness of the sample, and the previous history of the sample. There are certain applications of TGA. These are mainly the physical and chemical transition, loss of drying, purity and stability of analyte, determination of bound and unbound water begins at room temperature due to dry gas flowing to the sample. With TGA, determination of thermostability of both primary and secondary standard is possible. Studies pertaining corrosion is also application of TGA. There can also be automatic TGA. And lastly is the evaluation of suitable standards. That is the end of our presentation. Thank you.